Hello. Today I'm working on a project for a hammer mill. This is a badly drawn diagram of what a hammer mill looks like, and I have a customer who has a hammer mill, and he uses it to crush limestone. It's good for taking limestone that's not too big and crushing it down to fairly fine, like probably 1/8 of an inch and smaller, that he sells to a customer of his. Now, like I said, this is a diagram of a hammer mill, and essentially you have a drum. In this case, it turns at about 900 RPM. There's 6 rows of hammers. That's what these are supposed to be. Behind, on each row, there's 5 hammers in total, would be going into the board. So there's a total of 30 hammers. And essentially what happens is that just spins, and limestone is dropped in through the top. And as it falls in, the hammers strike it at the speed it runs. And with 6 rows of hammers, you get 90, well, there's hammers behind it, but you essentially get 90 rows of hammers passed by any spot per second. So it's pretty intense. There's, there's a lot of hammer blows per second when this thing's running at its normal speed. Anyways, the limestone would fall in, it gets struck by the hammer, and it shatters. It's different from jaw and gyratory crushers, which pinch rocks between heavy plates and essentially just apply an enormous amount of force which splits the rock. This is more just like swinging a hammer at something and shattering it, hence the name. So anyways, what I need to do is deal with the hammers themselves. My customer has had this hammer mill for a long time. He's always been able to get hammers from the OEM because they do wear out. But lately, he approached me 2 years ago about this. They started quoting him like 52-week lead times, essentially a year from the time he orders till he gets the hammers. And it's getting to be pretty long. And I think what's happening is he's starting to be concerned that if they're dragging it out this long, maybe the next few years they're just going to stop supplying hammers at all and just tell them, you're on your own. So he approached me about making new hammers for him. And he would like to, if we can make a hammer that works pretty well, then he can just get me to make them whenever he needs them. And realistically, I could probably supply him a set of hammers in about 3 to 4 weeks from the time he calls. So this video is about a little bit about the design, what I did to come up with a hopefully equivalent hammer, and then also the manufacturing of them. What you see here are 2 the OEM hammers. These ones are worn, obviously not new, and the one on the left was actually damaged. I believe the customer said a piece of metal got into the hammer mill and caused that to shatter and break off. But anyways, these are the original hammers, and this is what he didn't have a new one that I could use to design from, because he doesn't want to have to order from them anymore because it takes so long to get. So he gave me these, and he also gave me, he had a couple of drawings from the OEM of the hammer mill itself, and it was actually pretty handy because it showed a hammer in this view and one from this view, and there were dimensions not on the hammers themselves, but just dimensions in the drawings, and from that I was able to determine a scale for the drawing that I had that he'd given me, and I was then able to essentially measure and recreate the worn parts of the hammer that on these hammers are missing, and come up with a kind of a sketch or drawing of what the original hammer would have looked like. The construction of the original hammer consists of what I believe to be a steel casting. This makes the frame, This isn't overly hard. It can be marked with a file. You can see it makes up a large part of the hammer itself. And then on that, they braze a hard abrasion resistant casting. I assume it's some type of high chrome steel likely, and it's likely furnace brazed on, which is a good way of attaching it because you get a large amount of surface area, and then the entire hammer is bonded essentially. So even if you were to get a crack in this material, which you can actually see, there's one across here, on either side of the crack it stayed attached. Now it failed here, but these aren't really designed to be hammering metal. So now the sort of the things I had to consider when I was going to design my hammers were how I could actually make them and how would I get it to have kind of the same performance. The hammer is going to have a certain weight, and that weight will be somewhat important. It'll change as it gets used and it wears out. It'll obviously get lighter, but if I want to design it to be similar to a brand new OEM hammer, I need to make it weigh the same amount, but also where the center of mass is somewhat important, because that'll determine to a certain effect how much inertia this hammer has when it strikes. See, when the hammer strikes something, it can always rotate back on the pin slightly, and therefore the mass of the hammer and the position of that mass, the center of that mass relative to the pin, will determine essentially how hard it can strike something without going back too far. It's not a very good explanation of it, but it essentially, when the hammer strikes something, it may tilt back slightly from the impact, and you don't want it to, the more it tilts back, the less energy it's going to impart to the stone it's trying to shatter. So you want to have the same mass and have the center of mass in the same position as the OEM hammer if you're going to have similar performance. The other thing was that I had to consider was how was I actually going to make this. I'm a relatively small machine shop. I don't have a foundry. I can't cast this. I don't have a way of casting what's likely high chrome steel into this complicated shape. About all I can do is weld and machine. So in my design, I had to come up with materials that I could be confident that we could just weld and machine, that would hopefully give the same performance, and that wouldn't give us a bunch of problems with cracking and fracturing, because the last thing we want is for one of the hammers I make to come apart and now you've got a big piece of metal inside here, causing this kind of damage. So what I came up with was this. I'll just flip that over and get it the same position, orientation. So that's, you just see better if this is in the front. That's the hammer I came up with next to the OEM hammer. Now, mine is not worn. So mine, obviously isn't rounded off, it's square. The original OEM hammer was square when new. And the OEM hammer also, you can just see the remnants of it. It had a bit of a ski jump that actually came up quite high and then curved down quickly and down to the end. And that's what I've tried to sort of recreate in a rather crude way with these two pieces of Hardox. So I have a 3/4 inch Hardox as a sort of base plate for the abrasion resistant part, and then I have a piece of 1 inch Hardox which is there to mimic the original sort of ski jump type end that this hammer had. And then what I've done is I've welded that to a mild steel frame, which consists of two of these pieces. And then in between is just a slug of material, and its only purpose is to add weight to the hammer. I weighed these hammers, and then what I did, because they're worn out, so the weight I get from them is not the new weight. And not having a new hammer to weigh, the best I could do was take this sketch I had made that I'd scaled off the OEM drawing that I mentioned earlier, and then superimpose the worn out version of this hammer in that sketch, and then essentially calculate the missing cross-sectional area and multiply that by the width to get the volume of missing material. And then knowing the density, I could come up with a weight. And what I came up with was right around 20 pounds. And so I decided that's going to be the weight that my new hammers are going to be. And then when I went to design them, I kept that in mind. I essentially chose, like these were chosen to essentially try and mimic the hard cap here, this piece. And then the frames were chosen for their strength. They need to be to be able to withstand the centrifugal loads, but also to add weight. And then the final thing was I sized this slug to make up the difference, to get it up to 20 pounds. And it actually turned out quite well. We made a set of 6 for him, so he could just do some test fitting. And these are the other 5. And 4 of them came out to exactly 20 pounds, and 2 of them came out to 19.9. So we were actually pretty consistent. And that also, there's weldment there. My father-in-law, as kind of rough as it might look, he actually did a pretty good job of putting essentially exactly the same amount of weld on every hammer, because the weights came out very, very close on a scale that's supposed to be accurate to 1/10 of a pound. Got it pretty close. So now the other problem during the design phase was determining the center of mass of this so that I could have a similar center of mass on this. What I did was I put this up on a straight edge, and I shifted it around until I got it to balance. And then I know that the center of mass is directly above the straight edge. From that, I was able to measure over to the center of the pin. That's our datum for all these calculations and design criteria. Then just using the same method, I just used the same calculations over, the same numbers I got when I was trying to calculate the amount of missing material to get the overall mass. I was able to calculate the missing mass and then locate its center of gravity. And then you can do some, you can add, I can't even remember what the term is, but you can just, it's like having an assembly and each part has a different mass and its center of gravity is a certain distance away from a pivot point, and you can add it all together and come up with a single mass and a single distance to a common center of gravity, I guess you'd say. Anyways, I did that and got an approximation of where the center of mass of this hammer would have been when it was new. Again, if I'd had a new hammer, it would have been so much easier. It would have been 2 steps. Put the new hammer on the scale and record the weight. Put the new hammer on a straight edge and move around till it balances and measure the distance from that to the pin center line. And it would have been very straightforward. But without that, it involved a lot of calculation and estimating. And then when I designed this, I made sure that my center of mass was in the same location during the design stages. So now all of that is to try and get this to approximate this. And that's important. But what's more critical than that is that these be consistent when I make them. Because when this is spinning at that speed, the tips of the hammers are out at about 42-inch diameter. So you can picture something that's nearly 4 feet in diameter spinning at 900 RPM. There's a lot of centrifugal force, and if there's imbalance, there's gonna be a lot of shaking. So when he was buying the hammers from the OEM, they would come in matched pairs, and you were supposed to install them across from each other to keep the rotor balanced. So my goal is to make him hammers that are all the same weight, or if there's variation, to group them for him so he can install hammers of the same weight directly across from each other. And that was part of this consideration too. So but in the end, this is what I came up with. It's got, the mass is the same, the center of mass is the same. It has a pretty crude approximation of the original shape, and it is made out of an abrasion resistant plate, which I'm not sure if it'll be as abrasion resistant as this, but it'll probably be pretty good. And this is the thing, and my customer's fully aware of this, and he really wants me to go ahead with this. I told him multiple times I can't guarantee that it's going to perform the same, and he's not concerned. He just really wants to try it out and see. So so that's the sort of overview of the original hammers and the new design, and then I'll cover some of the manufacturing of them. The first part that's getting machined is a stack of blocks, and these are to make the slug. This piece here. Now, in the original 6 that I made him, I just got those flame cut out of 1 3/8 thick plate, because that's the spacing between here. When I went back to order more of it, they said they no longer carry 1 3/8 plate, and so what I ended up doing was getting cold rolled bar that was bigger here and here than I needed, and I'm in the process now of just machining that down to the correct cross-sectional, essentially just blocking it down. And that's what I'm doing on my it's my horizontal mill with a vertical head on it. And I got to take about 1/8 of an inch of material off, roughly. And with this setup, I can just do that in one pass. And that's the first step. And the only reason it's the first step is because I was able to get this material. I could just get it that day because it was bar stock. Whereas the rest of the pieces that I have to machine were laser cut, and they were a week away. So I started out doing this, and then I'll be doing the laser cut pieces next. So I got all the slugs machined on the one side down to 1 3/8, and now I have to set up and machine them for this dimension, and it's 1.736 is the target I'm shooting for. Because these are 1 3/8, two stacked side by side come out to just a bit less than 3. I got a 3-inch face mill in the mill, which means I can double them up and do 2 in 1 pass. So I've got 2 sitting in there on the parallels. I've already set the depth of cut, and now I just have to run them through one at a time. Unfortunately, in this setup, in the last machining step, I only had to take about 1/8 of an inch off, and I could do that in 1 pass. Here I have to take just over 1/4, and that's a little bit too deep for this face mill. So I'll take it in 2 1/8 passes. these are the laser cut frames. Right now I'm just in the middle of deburring them. We're making 24 hammers because I already built him 6 for a test fit. So 24 will round out the order of 30. So I've got 40 frames. So what we have here is the setup for machining the frames. So 2 frames side by side. I'm doing 2 at a time, mostly because I can. I have a 3-inch wide face mill, and these are 1-inch thick plates, so it's 2 inches. It's a pretty good fit for a 3-inch face mill. It makes it go a little quicker, and it also allows me to pair them up, and I'm numbering them so that I can use the same 2 in each assembly. It's not critical, but it's easy to do, and there may be some benefit, so why not do it? There's a little bit going on here with this setup. What I'm trying to do is machine this surface down. I've allowed extra material so I can clean it up, and machine this shoulder so that when the plate gets put on here, it's always in the same place relative. I'm using the end as a datum. It's in the same place relative to that. Once the plates are welded on, when I go to put the pinhole in, that's done from the end of the plates themselves on the fixture I have for machining, which I'll show later. One of the issues with these, when you get laser cut parts, is they sometimes have a draft angle. And what's worse than a draft angle is the inconsistency. They come sometimes and they have almost no draft angle, and sometimes they come and they have quite a bit. And the draft angle is simply this surface can be tilted up, because when the laser cuts through, it gets wider as it goes deeper, and it can cause an angle on here. Now, the problem with that is when you're trying to use one of those surfaces as a datum, which side do you use? And this is the problem here I've got drawn in my, now this is the 2 parts in the vise, looking from that end, sitting on parallels. And I've got this drawn highly exaggerated so it's clear, but this is the draft angle on each of them. And when you put them in the vise on parallels, the problem is you end up with a parallel on the left side of one part and on the right side of the other. And then you get this mismatch in height that I've got shown here. Now, the draft angle on these is pretty minor, and I don't have an accurately ground block that I can put in there, so it would catch. Essentially what would happen if I had a solid block across here, it would catch it here and it would catch it there, sort of like how I got it drawn there. These are 2 inches wide. I could put a 1, 2, 3 block in, but the problem is that the block is so close in width to the parts that when you clamp it down, you're not sure if you're clamping the parts or the block, and then the parts could be loose and then they could move when you're trying to machine them. I decided that it doesn't matter that much for this application, and the reason for that comes back to the balancing of the parts when they're rotating. So this is a hammer, and essentially what's important is the mass and then the distance from the pinhole to the center of the mass. And that requires 2 coordinates to specify. There's a horizontal distance to the center, and then there's a vertical distance from the center down to the actual center of mass. Now, when I machine this surface and they're not sitting perfect in the vise, I end up affecting the vertical distance of the center of gravity, center of mass, sorry. It doesn't affect the horizontal distance. Now, when this thing is rotating, what's actually the important thing is somewhere over here is the shaft that the drum rotates around. And then out here is where the hammer attaches to the drum. What's important is actually the distance from the axis of rotation of the drum to this horizontal distance out to the center of mass. That's going to have the largest effect on balance. And that is what you want to keep consistent on the hammers. I can't control the drum distance, but one has to assume that it's accurately made, because I can't imagine that with all the problems of balance you're going to have, they wouldn't make it accurately. And I have no control over it anyways, so all I can do is make my hammers accurately. The distance from here down, the vertical distance, has a negligible effect on that balance, for lack of a better term. Therefore, if these are out, maybe 5 or 6 thou, it's going to have essentially no effect whatsoever on the balance of this hammer relative to any other hammers. Where it's a little bit more important is the horizontal distance, as I just mentioned. So when I'm machining this and then this shoulder, I want to make sure the shoulder is consistent. And I'm using this as the datum for right now to machine the shoulder too. I didn't want to have that same mismatch when it comes to the position of these this way, because that will have a greater effect. It's still very small, but it'll have a greater effect than a vertical change. So what I've done is I'm using a 246 block as my stop, and this is that edge is, I've made it square to the vice jaws, and because it's the same width as the two plates, they end up sitting like this. So the high points touch and the plates are, not staggered like in this situation. Now, having said all that, one oversight, dumb move on my part, was while I allowed material here to be machined away, I forgot to add material here. This is actually laser cut to the correct distance within the tolerance that a laser cutter can hit. I should have added material there, and I will do that for the next round of hammers if there is a next round. But what I did, I do want this to be machined for placing the blocks, so it's more accurate again, because the horizontal distance is more important than the vertical. So what I've done is I've actually taken I have the measurement from here to here, what it's supposed to be. I'm already there with it being laser cut. I'm moving in about 15 thou, changing that dimension slightly just so this will clean up. And these are the results you get. Most of it cleans up. You get an odd little bit, but that doesn't matter. I'm looking for a good surface for the part that has to be welded on to butt up against. Anything that's below that surface has no effect on it. So that's an okay result. The result is that my horizontal dimension changes slightly. That's in the sensitive or bad direction, you might want to call it, for balance. But that isn't quite so as important as all of them being the same, that all the hammers be consistent. That's the most important thing for this balancing. And the fact that my original 6 hammers, which are down here, may be slightly different than the 24 I'm making, that's also not a concern, because it's an even number. Each group is an even number, and therefore you can always place 2 members of the same group opposite each other, and they will cancel each other out or balance, however you want to say it. If I had 5 hammers of one size, 25 of the other, it would be a problem because I'd have 2 opposite each other from different groups, and they may be slightly different. So in this case, it's okay. I can see that if these hammers do work out, and a few years from now he wants a second set, we'll be building all 30 at once. I will allow extra, and they will all be a bit more consistent than this. Even though the reality is it doesn't matter as long as you have essentially all that really matters, as long as you have 2 hammers that are the same as each other. As long as there's always a pair that are the same, you can always put them opposite of each other. So anyways, that's the thinking that went into the setup, and I'll show some of the actual machining. These are a little more awkward to put in the vise. The reason for that is that this part is flat, and then there's a slight radius, and then you get the angled part, and obviously the parallels have to sit here. You want to have as much of the parallel under there as possible, but you don't want it to start climbing the ramp. So it's a little more buggering around than if you got a surface that's just flat all the way. Try that again. It's good. Parallel is still just slightly loose, but I cannot feel any vertical movement when I try and rock it up and down. So for this, that's close enough. first part of that cut is just to do the top part of the shoulder. The insert height on this face mill is just a little bit less than the shoulder height, and I can't actually do it all in one pass. So I just take a pass, get the top half done, then I come back in and I set the depth of cut to get this at the right height, and go through again, and then just come back to get the third pass is just to get the rest of it off. Although you can see machining mark overlap, you can't actually feel anything. So the head's trammed in pretty square to the table. So it's giving good results. Well, I think we'll bring video 1 to a close. We discussed the reason for the hammers, the design considerations, and the pre-weld machining steps. In video 2, cover some of the welding and the reasons, some of the design considerations there for the way we welded it together, and the post-weld machining. And then I hope to make a third video of them actually in operation once they're installed in the hammer mill. I won't really be able to see them as they're spinning because it's all closed in, but I'll be able to see what kind of output we're getting from the hammer mill, and find out if it's equivalent to what it would do with the OEM hammers. Anyways, we'll see you in the next video. Bye. Thanks for watching.